The progress in computational capability that we've experienced in our lifetime is nothing less than breathtaking. It has transformed all aspects of our existence. Just to give you a sense of what we've accomplished, the fastest computer in the world today is more than 18 million times faster than what was considered the fastest computer in the world 30 years ago. This is part of why we can run some of these sophisticated AI systems today. But what's even more remarkable is not just that this is possible, but that economic and commercial incentives are aligned to make this technology widely accessible, and not just to a select few. My 3-year-old cell phone, which you could probably get for free with a new plan, used to be called a supercomputer not very long ago. Because of all this progress, today we are at the fundamental limits of what we can do with current silicon technology. And as a result, we are facing a major shift in the way electronics is designed, where we are trying to move from general purpose computers, like our laptops, to computers that are specialized and whose operation is tailored to specific tasks. Companies like Microsoft, Google, Meta, traditionally viewed as software houses, are now developing their own hardware that's tailored to their specific needs. The reason for this is actually quite simple. It turns out that customization of hardware can provide something like 1,000-fold additional improvement in efficiency, which is an astounding factor. Historically, this was viewed as the last resort, pursuing customization, simply because what that meant was if your requirements change, you needed to build new hardware. And hardware design today is an extremely time-consuming and costly process. My research group is exploring 2 approaches in the pursuit of ever more efficient computation. The first effort we are undertaking is on reducing the time it takes to design customized electronics. The reason it's expensive is you have to pay a lot of people for a large amount of time. We've developed a framework for chip design that aims to bring down the time to design a customized chip to something like days or weeks, rather than the 18 to 24 months it takes today. And this approach is actually enabled by an unconventional way we are approaching chip design that allows us to leverage decades of experience in software development techniques and use those to translate algorithms into efficient chips. The second avenue that we are pursuing is to draw inspiration from nature, in particular by leveraging what little we really know about how the brain works. The human brain uses roughly 20 watts of power and can execute computations that we can barely emulate using megawatt scale cloud computing systems. So can we build computers that could be as efficient or even more efficient than what our biological brains can compute? What happens if instead of just trying to build a regular computer, we try to build electronics to mimic the structure of neurons and synapses? Could we then design electronics that could actually interoperate with our brains, right? Potentially augment them? Or be used to, say, heal damaged regions in the same way that we can repair fractures with mechanical supports? In search of pursuing this goal, we've built a large-scale electronic system that mimics simple models of neurons and synapses of this type. But it turns out that the big issue is that we actually don't understand how biology solves a range of problems, and that's a completely open area of research. This becomes even more challenging when we want computer systems that satisfy qualitative attributes. For example, we'd like the systems to be, say, ethical or unbiased. And it's kind of hard to expect a computer can do this when we can't agree on what that means amongst ourselves. To make some of these ideas a little more concrete, we are working with the Yale School of Medicine on a collaborative project where we're trying to design customized electronics to interact with the brain. The short-term goal is quite straightforward. We are trying to develop implantable electronics that could help patients with neurological disorders. The application we are looking at first is epilepsy, where, for example, you could run sophisticated algorithms that in real time could detect the onset of a seizure and try to take corrective measures. The system's designed to be programmable, so a doctor can customize it to the needs of individual patients, modify it as medical techniques evolve, and perhaps reuse the same platform for other applications, say Parkinson's. Working with surgeons is nice because it means we can have them decide what is ethically appropriate. I don't have to worry about it. Surgeons actually have to do this on a regular basis. But imagine if we could build such a system that can interoperate with the brain, that can be programmed and adapted over time, customized to the needs of individuals, how do we know if using it is appropriate? It's going to change over time. Even say the limited case of a specific disorder, how do we obtain FDA approval? Right? These are all interesting questions. As we develop technology to benefit humanity, we are confronted with complex challenges. And the potential benefits are incredible. What you can see in the public domain is just the tip of the iceberg of what we know already how to do. But it's up to us to make sure that we use the technology in a responsible manner.